This is an Algebra 2 class where we're working with graphs and applications for exponential functions that have a natural base of e. E, if we remember, is an irrational number like pi. Its value is approximately equal to 2.71828, and we have the dots to show that this number continues without end or without pattern. But really, e is a constant, just like 2 or 7 is a constant, and it behaves in the same way. So let's see what the graph of y equals e to the x would look like. As we look at it, first off, identify that e is our base, and that value e is greater than 1 because it's about 2.718. So we know that we are going to have a growth graph. And as we're looking at exponential functions, we know that the domain of all exponential functions is going to be all real numbers. The range for an exponential function in its simplest form, the parent function of y equals e to the x, is going to be y is greater than 0, and we're going to have a horizontal asymptote of y equals 0. To see a more exact shape of that, we're going to plot a couple of points and see what it looks like. So for x, we're going to choose from -2 to 2. When we substitute -2 in, e to the -2nd is about 0.14. E to the -1st is 0.37. E to the 0 is 1. E to the first is e, which is, as we said, about 2.72, 2.718, so we'll go 2.72. And e to the second is about 7.39. We're going to graph those. So let's just take a look at a graph of those. Our x and our y. At -2, we're barely above the x-axis. At -1, we're at 0.401. 1 is at 2.7, and 2 is at 7.4. So as we connect it, remember it slides in right next to the x-axis on one side, getting increasingly steep as we move to the right. Make sure that you get that shape. Okay, so that's the graph of y equals e to the x. Really, it doesn't look much different than y equals 2 to the x or y equals 3 to the x, just somewhere in between those two. Now, let's take a look at simplifying expressions involving e. E as a base follows all the rules of exponents. So for instance, here in our first example, we have e to the -2nd times e to the 6th. We have a common base of e, so our rule when multiplying with a common base is to add the exponents. So we're going to go e to the -2 plus 6, or e to the 4th. Our next example, we have a quantity raised to the -4th power. Everything inside the quantity has to be raised to the -4th power. So we're going to take 2 to the -4th and e to the -2nd to the -4th. Our rule here is to multiply exponents, so we have e to the 8th. Using our rule for negative exponents, our term with a negative is going to go down into the denominator. So we have e to the 8th over 2 to the 4th, or e to the 8th over 16. Our next example, we have 3 terms multiplied together. They all have a common base of e, so all we need to do is add our exponents together. So we have e to the power of x plus -3x plus 2, or e to the -2x plus 2. We're going to leave it at that form because I don't know whether I've got a negative value there or a positive value, so e to the -2x plus 2 is how we're going to leave it. The next one is a division problem, and we have a 6 over an 8, which reduces to 3/4. And then for our base, we have each one here with a base of e, so we want to subtract our exponents, so we're going to take 4x minus 1x. That gives us e to the 3x. Our next example involves a square root, and a square root is another way to write an exponent of 1/2. So this would be e to the 2x raised to the 1/2 power. Then we use our power rule by multiplying exponents. So 2x to the 1/2 power is 2x times 1/2, or e to the x. Another thing we can do with working with e is we actually have a calculator button that allows us to approximate values of e. There's 2 places on your calculator where we can find e. On the left-hand side, it's a second function key above the key that says ln. It's an e to the power of x, and on the right-hand key, or the right-hand side, it's above the division sign. So the first thing I want to do, we want to evaluate these to the nearest thousandths place. So I'm going to do e to the third, second, ln button gives us e to the power, and we go to the third. So to the thousandths place, that's the third place past the decimal, so we have 20.08, and our 5 here has a 5 following it, so it goes up to 6. Our next one has -4 multiplied by e to a power. So let's do that here. -4, second function ln, and we're going to raise it to the 3.8 power. So we get very large, very small, -178.805 to the thousandths place. Okay, the next thing that we can work with looking at or working with e is recognizing with functions with a base of e whether they're growth or decay functions. In our example number 8, we have y equals 2 times e to the x. Our base is e, and remember e is 2.718, so it's definitely greater than 1. We have a growth graph. Our next one, number 9, is y equals 5 times e to the negative x. Remember, with a negative exponent, that does the reciprocal raised to the power of x. So 5 times the base of 1 over e raised to the power of x. Well, 1 over e is about 1 over 2.718. We know that number is less than 1. It's almost 1/3, so this will be a decay graph. Our next one, we have y equals 1/2 e to the 0.2x. Well, this can be rewritten as 1/2 e to the 0.2 raised to the x. So our base is e to the 0.2. How big is e to the 0.2? Is it greater than 1 or less than 1? Well, we can go back to our graph, and we notice right here, when x is 0, we have 1. So any exponent greater than 0, our value of e to that power is going to be greater than 1. So e to the 0.2 specifically is going to be a little bit larger than 1. So in this case, our e to the 0.2, our base, is going to be greater than 1, so we have a growth graph. Now, one of the examples or applications of natural base E is in our continuous interest rate formula. When we take the compound interest formula, we have A equals P times 1 plus R over N raised to the NT power, and we want to continue it or compound it continuously. This part right here gets closer and closer to the value of E, and so we end up writing this A is equal to P times E raised to the power of R times T. Okay, let's compare what happens if we compound it on finite periods of time, like once a year, twice a year, 4 times a year, 12 times a year, as opposed to compounding it continuously, like all the time, every minute or even every second. So we want to find the accumulated amount of money in an account after 10 years when the account was started with $2,500 and it earns 2% annual interest rate. In our first method, we're going to compound it monthly. So that's our compound interest rate formula. We know that A is equal to P times the quantity 1 plus R over N raised to the NT power. So let's identify our parts of this formula. We want to find the accumulated amount, so we're looking for A. It says after 10 years, so T is 10. Starting with $2,500, so P is $2,500. Our interest rate is 2%, and 2% is the decimal 0.02. And we want to compound monthly, so N is equal to 12. Let's plug those numbers in and see what we get. So we have A is equal to 2,500 times 1 plus 0.02 over 12 raised to the 12 times 10 power. We plug that into our calculator and we get $3,053.00. Let's work this problem again using the compound interest rate formula, which is accumulated amount equals principal times E raised to the RT power. So again, our P is equal to 2,500. The R is 2%, which is the decimal 0.02, and our T is again 10 years. So plugging those in, we have 2,500 times E to the power of 0.02 times 10. This part is all in the exponent. So we want to multiply using that exponent. And let's see how that works on our calculator. Let's plug those values in. I'm going to do it right over here. So we have 2,500 times E to the power of 0.02 times 10. And we get $3,053.51. A little bit more when we compound it more frequently. One of the other uses of exponential functions, of equations of this continuous growth formulas, you'll see this in your science applications when you talk about radioactive growth or decay. So we also have many applications in that sense. Okay, so these are applications and graphs of exponential functions with a base of E.